So Coke is written in, as I mentioned, Coke is written in OCaml. I don't know any OCaml, so this will be probably the hardest to take a look at. Welcome to part 3 of our look at theorem provers. We're currently looking at Coke, which is written in OCaml and is slightly, by just a few years, I think, the oldest of the ones we're going to look at. So it's 52% OCaml, but also 44.7% Coke. I think that it's a little bit, it's pretty similar to Agda, but we'll see. And I don't know anything about how OCaml is laid out. We have pre-typing. I don't know if that's part of, if that's like a fundamental part of this project. We have tactics. This is also the only theorem prover I've really used. I worked through like the software foundations book, I think, but I've never really thought about its source code. We have theories. I don't know what top level and top bin are. Also, this is ants are everywhere, which I don't think I've said. Okay. Do you have something like a source directory? Maybe not. We have STM, maybe software transactional memory, pre-typing, parsing is going to be parsing, maybe library, lib, or kernel. Interp might be important. This Coke IDE should be IDE support. Engine might be important. Gramlib, maybe grammar library. Coke PP. There's a long history, I think, of French mathematics of naming things in a way that are it would make like English users giggle. I think Coke PP is maybe in that vein. Okay, so what's in pre-typing? I don't know. We've got some combinators, some coercion no ops. So this does look pretty interesting. STM is what? This does look like it's probably software transactional memory. We've got some asynchronous stuff, some DAG stuff. DAG presumably being directed acyclic graph. Dune is the OCaml buildy tool, I think. Let's look at stm.ml. We got a nice ASCII comment box. I guess that's a rooster or a cock. And we've got some stuff here like TAC error filter, async proofs, cache. This is interesting. Forward feedback. We've got some mutex here. I'm not sure what ref is. This is some sort of function with a doc ID and a span ID. I guess maybe feedback in the sense of possibly giving the user feedback as opposed to feedback in the control theory sense. Let's see if I can find anything about it. Tactics. I guess it doesn't want to load. Okay, it loaded. Let's see if I can find the word feedback. We get a search bar? Yeah. Yeah, like faster feedback. I think this is like feedback in the sense of like information about how you're doing on proofs. Okay, so that's probably mildly interesting, but we're not going to focus on it. Okay, so here's tactics, which is a big part of Coke. Here's theories, which look like we're probably doing mathematics. We have arith, presumably arithmetic, logic, MSETs, and arith, relations, setoids, I thought I saw. Maybe not. Maybe I hallucinated. Here we go. It's blocked by my microphone. Omega. Like the ordinal. Omega functions. It's not the big O notation, I don't think. The prime omega function. Absolute infinity. is an extension of the idea of infinity. Yeah, this is probably what it is. Maybe. And we have lots of stuff. Like we have module Z. This syntax is not super readable, but it's very terse. So we have some lemma. Whatever mod 0rx xy. I don't know what colon means in this syntax. Y equals 0 implies x, maybe? Y equals 0 implies x mod y is equal to x. Oh, okay. So this is the name, mod 0r xed, I guess. And x and y are presumably the arguments. And this is, I guess, the statement of the thing we're trying to prove, that if I'm taking this to be a conditional, that if y is 0, then x mod y is x. And here's the proof. Intro, this is, I think, in the tactics language. I forget what intro does. Subst destruct x. So I don't know what all of these are doing, but basically we're plugging something in, I think, and then taking the thing that we plugged in, and I think destructing is maybe a little bit like pattern matching, like maybe get the thing that take the combined expression and get some subpart of it. And then reflexivity is presumably something along the lines of x equals x ultimately. And then QED is presumably just some symbol that says like we're done. Here's some more. I forget what LTAC is, but this is pretty big table. It's hideous, so let's look at it. So LTAC, Euclidean division equations cleanup. So some, maybe the Euclidean division algorithm. And we're cleaning it up somehow. And this is defined to be, we're going to repeat some stuff, I assume. Repeat match goal with, I don't know what these vertical bars are. I guess they probably either delimitate something or we're doing like a pattern matching syntax. This is, or maybe one vertical bar is the pattern matching syntax, and maybe this vertical bar is the set builders, is a bar from set builder syntax or something along those lines. This is maybe like a set with H. As long as question mark X is between 0 and blank, such that negative blank, or I don't know what this is going on. They're going to destruct H. And then we're going to call repeat match goal with again. And we've got more of these H's, these things that will possibly be sets. And on the right-hand side, we have lots of clear H's. And I'm guessing this means like no matter what X is or whatever, or maybe that's what underscore means. I don't know what this diamond is, less than and greater than perhaps, or some other meaning, but no idea. Okay, but it's some big table. I'm cleaning stuff up. Okay. Moving on. So top level, we have things like compile, coke loop, coke top, load. This looks like maybe more like compiler or interpreter stuff. Quantum. Perhaps. You can, if you want to make a suggestion, you can, there's a spreadsheet on the Discord where I'm keeping track of the suggestions. I don't know what vernac is, maybe vernacular or something or other. Parsing of vernacular. And I'm not sure what the Coke vernacular is. Oops, I misspelled the name of the thing. Is it the same as Galena? So the Galena specification language. This chapter describes Galena. the specification language of Coq. It allows developing mathematical theories and to prove specifications of programs. The theories are built from axioms, hypotheses, parameters, lemmas, theorems, and definitions of constants, functions, predicates, and sets. The syntax of logical objects involved in theories is described in section terms. The language of commands, called the vernacular, is described in the vernacular. Okay, oh, we get a whole, we get like the syntax. And we have things like decorated sentence, sentence, and assumption. And a sums, definition, proof. A proof is a thing that I guess maybe starts with proof and ends with QED, or maybe defined and admitted. I don't know if that's what that syntax means. Grammar is the word I was looking for. Okay, not syntax, the opposite. Okay, let's. So here's Vernac. That might be interesting. Let's leave it open, but I also want to see what else we have. So Cook, bin, byte. This is maybe like more like under the hood stuff and less about math and types. Library. We have things like locality, summary. That may be important, but we'll just kind of move along. Lib has things like acyclic graph. C-ast, I'm guessing abstract syntax tree. Errors, D-ast. I don't know what C and D are. Warnings, control. That might be interesting. I guess I'll open up some of these. I forget which one is the types and which one are the implementation. I'll open these MLA files. I think, now that I'm thinking about it, maybe I is the implementation. We'll open D-ast and what, C-ast. Just open a few. Here's the kernel. We've got lots of stuff, declaration, entries, environment, and so on and so forth. Interp has abbreviations. There's lots and lots of stuff here. Smart locate, and then engine. Now that I'm thinking, so we saw name gen in lean. I'm guessing name gen is because like we're doing, as part of theorem proving, we're creating lots of like new hidden variables. And I think like things like x_1 and x_0 as things get like renamed and whatnot. So I think that's probably what name generation is about. I don't know what univ names are. Univ minim. We're seeing a lot of things that are named similarly between Lean and Agda and Coq. And so I'm guessing that they learned from each other. We have some grammar here. Stream. I don't know what plexing is. And here's Coq PP. Maybe pretty printer, preprocessor. I'm not sure. We'll ignore it. And then here we are into the actual implementations. Look at, here we go, pretty printing. All right, ignored. D-ast, you've got some thunks. So this is some functional implementation stuff, I guess. Let map thunk. I don't know what this notation is. Type S, F, I guess. I'm not sure what this means. Maybe a constraint on the type of S. So F, is this the type signature? So underscore, I don't know what the blank underscore is. S, thunk. No idea. But I think this means if X is a value, then we're going to return value of F applies to X. And if K is a thunk, then we're going to return thunk of lazy of F lazy.force K. I don't know where K came from. F is here. Who knows where K is? I don't know. Okay, so this is something about thunks. Let's ask the AIs. So tell me about this syntax in OCaml. For example, where does K come from? And K comes from, okay. So let is the definition, because the definition, the map element is the name. Type S introduces a locally abstract type S. This is a way to specify that S is a type variable that will be used within the scope of this function. Okay, so it's a type variable. Is that... Let's look up OCaml type variable. The type expression underscore stands for either an anonymous type variable or an anonymous type parameters. In data type definitions, type variables are names for data type parameters. In type constraints, they represent unspecified types that can be instantiated to any type to satisfy the type constraint. Yeah, I'll read this later. Okay. F is for blah, blah, blah. So this underscore S thunk to underscore S thunk, it specifies the type of the function map thunk. Underscore S thunk represents the input type of the function. The underscore is a placeholder indicating that the first type parameter of the thunk type is not specified here. And then we have the pattern matching. Thunk K. If the input is thunk K, it forces the lazy value K. I guess K is anything matched by this. The K is the value contained within the thunk constructor. Okay. So we're just unwrapping the thunk, and the thing that's inside we're naming K is, I guess, what that syntax means, which makes sense. Here's CAST. The AST type contains generic metadata for AST nodes. So type, I don't know what this prime is, prime AT. V is maybe value, which is the type of the first thing here. And loc is, I guess, a location in the code. Because we're building an abstract syntax tree. So how is CAST different from DAST? Where did DAST go? I'm not sure. DAST is opening CAST. I don't know. CAST seems like the more, like it's actually implementing an abstract syntax tree, and DS looks maybe more like it's doing stuff with thunks, but I don't really know. So univ names is, we've got this universe binders type. We've got whatever qvar is, and an identity ID map level. So this is information about binding. The map, I'm going to guess, is mapping maybe the variable names to the binding. We're keeping track of the level. And rev binders is possibly like the reverse match. And whatever qualid level is. Qual ID of level? I don't know. Okay, univ minim to disallow minimization is set. I guess this is something about minimizing. Choose canonical, lower union, lower add, find inst, universe map find v view L bound. I don't know what we're doing. I guess some kind of reduction. I don't know. But we're going to move on. Here's grammar stuff. Grammar for which language? I'm not sure. I think there are multiple languages, like the tactics language versus the other non-tactics language. I don't remember which one is which. But we have a bunch of types. This thing is like a reader of grammar state, reader of keyword state, reader of entry state. A module parsable. These are presumably things that can be parsed. You've got line of code, consume, which is a function that takes a t and an int, and it returns unit with kw state, maybe keyword state. We have module entry, which can make, parse, I guess, get a name. Given a prime a and a t, you get the name, I guess, of it, the string. And symbols for either an endterm L, a list 0, a list 1, opt, self, next, tokens, rules. So this does look like grammar stuff. I have no idea what is going on syntactically with OCaml. We've got lots of primes and lots of A's and so on. A production is presumably producing something for the grammar or something similar. Stream? I don't know what stream is. You can peek inside a stream, and we've got scons, which is maybe going to call cons with sum. And we have sgen. And we can, it's like a, maybe it's like a list with some operations like peeking inside of it and adding stuff to it and so on. Plexing, I don't know what plexing is. It's lexing. Lexing for camel P5 grammars. Archery is a type of regular tree with nodes labeled by values of type A. Let's ask the AI, what does a type with A mean? Such as tick A. Is it a tick or is it a single quote? First of all, let's get that right. It's a single quote. Represents a type parameter that is polymorphic. This means that the type can be instantiated with any type. Okay. So it's like a type variable in Haskell, I guess, if that's the right word. So our tree is some regular tree with nodes modeled by values of some type. The implementation uses de Bruijn indices. So binding capture is avoided by the lift operator. Note that it differs from standard regular trees by accepting vectors of vectors in nodes, which is useful for encoding disjunctive, conjunctive recursive trees, such as inductive types. Okay, so this is all building stuff, I think, for the compiler and for the grammar. That's all cool. Let's look a little bit. Here's the vernacular stuff. I want to look at least a little bit at the tactics, and I want to look at some of the math too, see what we can find. Here's tactics ML, tactics MLI. And I guess open is probably the OCaml version of import. We have tickle evars. I don't know what. Is TCL something we saw in the other one? I'm not sure. Some stuff about declaring Boolean options, some errors. These are all exceptions. Clear dependency message. Tactic interp handler. Interp error handler. So this is all for error handling. Then we have tactics, starting with primitive tactics. Unsafe intro. This tactic creates a partial proof, realizing the introduction rule, but does not check anything. And let's look at it. So unsafe info, and I guess it gets an env, a decal, and a b. Decal, maybe declaration. I don't know if that's the expression we're working on. And I'm assuming, what? Is this a I don't know if this is some sort of condition, but we've got this refine with principal tilde typecheck false begin fun sigma, and we'll let context equal named context val env in. So these are just, I guess this is just, we're assigning variables. So nctx is push named context val on decal context. So we're getting the named context value, we're pushing it somewhere, and we're calling econster identity substitute val. So I guess we're substituting the identity something or other, or maybe just substituting the identity of a variable. I don't know. And we're calling const on make rel, maybe make relation on one inst. Where did inst come from? Inst come from doing this identity substitution. And then we're calling subst1 on make var named decal get id decal b. And then we're calling new pure evar on the end context, which is, I guess, the context that we got somewhere. So it's a context that we got by taking the environment and pushing pushing the decal onto it. And whatever this is. So we're calling a new pure evar on that context, and then sigma and nb. Sigma came from here. NB came from this substitution. And then we've got this thing at the end, which seems to be a tuple. Maybe that's the thing we're returning. It has sigma, make lambda or let in, named decal to rel decal make var ev inst some var. I have no idea what any of that does, but that's a thing you can do. And then we have more tactics. I don't know if this is, I guess this is OCaml because this is a .ml file. And I just don't know what any of these functions do. There's intros in here. You have intro. So intros is intro forthcoming last, then gen id.set.empty, false, none, 0, and this is maybe a lambda, a function of doesn't matter what, and I guess tickle id tac. I don't know what tickle id tac is. It's some tactic. Yeah, I'm trying to see if I can find out where it's defined. But again, not knowing the syntax of OCaml, it's hard to see what is the definition. I'm not sure. Also, what's up with TCL? Let's see if I can find some documentation on the internet. Coke Refiner, legacy proof engine. The tickle ID tag is the identity tactic without message printing. Okay, so what's up with Coke and tickle? I don't think it's I assume it's not the language tickle, but who knows? Tactic something? Okay, so what else can we find? We'll ignore pre-typing. We were going to look at math. How much? We have 1 minute left. Well, I'm not sure that's going to. We'll do a quick look at math. Where was it? Library, maybe? I think there was like algebra, but it was heavily abbreviated. That's continuous integration. Maybe theories. Let's look in theories. And what do we want? I'm not sure what an F set is. Q Rth. Maybe we'll look at reals. But I kind of want to know what an F set is first. F set facts. F set list. F set weak list. F maps. I don't know. How about we check out reals? How about Cauchy? Constructive Cauchy abs, constructive Cauchy reals. Let's look at constructive Cauchy reals. We're going to import. We've got this require import stuff. What language are we in now? We are in the .v, which I guess is the vernacular. And we're importing Q arithmetic, Q power, Q abs, Q round, I guess rounding, and whatever constructive epsilon is. Constructive epsilon. So constructive epsilon says this provides with a proof of the constructive form of definite and indefinite descriptions for sigma 0, 1 formulas, hereafter called small formulas, which infers the sigma existence, i.e. type existence, of a witness to a decidable predicate over a countable domain from the regular existence, i.e. prop existence. Koch does not allow case analysis on sort prop when the goal is not in prop. Therefore, one cannot eliminate exists and Pn in order to show I don't know what these brackets mean, but the n is a natural number such that P of n. However, I guess the brackets are just these documentation things. However, one can perform a recursion on an inductive predicate of sort prop so that the returning type of the recursion is in type. Okay, so we're importing constructive epsilon. Also C morphisms, whatever Leah, LQA, Q extra, constructive extra are. The constructive Cauchy real numbers, i.e. the Cauchy sequences of rational numbers. Cauchy reals are Cauchy sequences of rational numbers equipped with explicit moduli of convergence and an equivalence relation, the difference converges to 0. Okay, so I just want to see a little bit of like how these things are defined and if they have proofs, some of the proofs. So definition, a Q Cauchy seq takes xn of type, I guess probably they'll take an integer, they'll return a rational. Xn, I guess the thing that makes them a sequence is that you're indexed by n, and the z argument is maybe the index, such that for all, so there's some prop. I don't know if prop is the same as theorem or if like prop is different in any way. For all k in z and pq in z, this must be a condition. So maybe the first thing, or the conditions, and maybe comma separates the conditions, or not. We'll see. If I assume this means that p is less than k, this seems like a second condition. Q is less than k. Then the q absolute value of xn at p, I guess the pth x and the qth x is less than 2 to the k. So for all k and z, k should be Shouldn't P and Q be bigger than K? Maybe I'm reading Z.LE wrong. I think that what this is saying is that for each K, we can maybe find, no, for every P and Q that satisfy these, that as we get, this should be like, as we get far enough along in the sequence, then the numbers that are at the end of the sequence are close to each other. Let's look at what Z.LE is. Is it Q arith? What did we import here? Q round, Q abs. Probably Q arith. Oh, no, Z.LE. Just look up Z.LE. Is there a Z arith? Maybe Z arith base? Yeah, this is turning into a maybe Z order. Yeah, I'm not sure. At any rate, we get more stuff. So serial is a thing that I guess I don't know where make real is defined, but we're going to call make real on a sequence of from Z to Q. So the Z is the index, and it's a list of, it's really an infinite list of rational numbers. A scale, which is the integer, maybe, I don't know what scale is going to be, but perhaps recording some large enough Z. A Q Cauchy seek, and a bound. So what is a Q Cauchy seek? A Q Cauchy seek is the thing we were just looking at. And okay, so this is so Q Cauchy seek of seek is a condition on this sequence, and Q bound seek scale is a condition on scale. So Q bound takes in a list of rationals and a scale which is of type integer, and it satisfies the following property. For all k and z, so for every integer, the absolute value of xn at k is less than 2 to the scale. Okay, so the scale is like, it's just big enough to kind of bound the worst of the Cauchy sequence in some sense. And then let's see what else. That's what the serial is a record with all of this stuff. This is basically this is constructive. So we have not only the Cauchy sequence, but in some sense we have, maybe if not like if this, I think this is saying really that we're perhaps recording the proof that it's Cauchy. And so like as we transport the reals around, we have like a proof of that they are Cauchy and that they satisfy this bounding condition. Here's C real LT. We have X and Y that are C real. We're gonna get a set, which is, I guess, all of the integers such that the following is true. We're gonna call QLT of 2 times 2 to the n on the nth number in the sequence, the nth number of the Y sequence minus the nth number of the X sequence. And I don't know what QLT is, but something about kind of like a difference, maybe like kind of like a normed difference between them. All right, so that's the Cauchy reals. Let's see if we have the Dedekind reals. Or not. Here are the classical Dedekind reals. Let's look at that, just for funsies. Now we have a bunch of lemmas, some Q fixed point lemma. We have Dedekind cuts, classical Dedekind reals with 3 logical axioms: funnext, sig for all dec, and sig not dec. The lower cuts defined as functions from Q to the Booleans have all the classical properties of the real numbers. We could prove operations and theorems about them directly, but instead we notice that they are a quotient of the constructive Cauchy reals from which they inherit many properties. Okay, so they're going to define, I guess, the proposition. They're going to define these, I guess, as Dedekind reals, and then like for proving the propositions, they reuse the Cauchy reals, or perhaps they don't prove them at all, but I'm not sure. And this is much longer than the Cauchy reals. I would have thought the Dedekind ones would be smaller than the Cauchy ones, but this seems like that's a thing. And I still kind of want to figure out if there's a way to let's see if I can find LT like this. Yeah, LT is less than. Wait, what? LT maps to greater than. Yeah. All right. Well, whatever. Okay, so that is Coke. And that ends our exploration of the source code of theorem provers. Like I said, at some point we're going to start using theorem provers. We're still in the part of this this channel where we're writing code. I'm still working on getting kind of just a proof of concept Haskell app to try to just verify for myself that we can build reasonable, like user-facing stuff in Haskell. Using Haskell, you can build a lot of cool stuff like compilers and parsers, and we've seen a lot of that. It's sometimes used for things like filters, like maybe like spam filters, and it's also used for things like writing programs that have some kind of like logical assurances. But so far, as far as I can tell, it's not used much for just kind of the standard user-facing apps. And so I kind of want to make sure that I get a sense of how that can be done. And then over time, we're going to expand our use of Haskell and Haskell-like languages to include more stuff like Agda or Idris, or possibly Lean, and that sort of thing in the future. So that's all for now. Thanks for watching.